Hi everyone, can you hear me all right? Okay, cool. I'm Ruby Byrne. I'm a physics PhD student at University of Washington, and I study cosmology. So what that means for me is I use telescopes to try to uncover signatures from the early universe to understand a little bit about what the universe looked like a long time ago and how it evolved. So this is important for a few reasons. The first being is it's important to understand where we came from and where everything around us came from. But there are also some unanswered questions in modern physics that we could potentially answer if we had a better understanding of the evolution of the universe. And these are things like the origins of antimatter and the nature of dark matter and dark energy. Oops. There we go. So first off, I'm going to tell a story of two American astronomers named Arno Penzias and Robert Wilson, and here they are with their telescope in New Jersey. So these astronomers made an extremely important discovery in 1964 that really changed modern physics forever. While looking at the sky, they noticed a faint glow coming in every direction. At first they thought maybe this was a problem with their telescope or with their data analysis, but they eventually realized that it was something very profound. And it was so profound that it earned them the Nobel Prize in 1978. Now some of you might know what it was that they saw, especially if you've taken some physics classes, but if you haven't, you certainly will by the end of this talk. All right, so our story starts here with hydrogen. Hydrogen is one of the fundamental building blocks in the universe, and it consists of two things: a positively charged proton that's surrounded by a negatively charged electron. So this is the chart of all of the building blocks in the universe, and because hydrogen is the simplest of all, it has a very special place in the upper left-hand corner right there. Out of all the normal matter in the universe, hydrogen makes up 75%. Another 23% of all the normal matter in the universe is helium, and helium is the second most simple building block, and it has a special place in the upper right-hand corner of the periodic table. All of this other stuff, all of the carbon, the oxygen, the silver, gold, lead, all of that stuff makes up just 2% of all the normal matter in the universe. So because hydrogen makes up so much of the universe, it's the most important when we talk about the universe's evolution. And it comes in two states. This is its normal state, where the proton and the electron are tightly bound together. But they can also get separated. I think of it a little bit like the electron is a hat that the proton wears, and that hat can get knocked off if the hydrogen bumps into something hard enough. Normally when this happens, the proton will go around and find its hat pretty quickly and put it back on, but there's certain cases where this doesn't happen, and I'm going to call these mosh pits. So this is where a bunch of hydrogen goes to see their favorite punk show, and they're really into the band, so they all cram up really close to the stage, and they're moving around very quickly and have a lot of energy. So when their hats fall off, they can't put it back on again because it's hit again too soon. So it's just this constant process of being hit. So if you've ever been in a situation like these hydrogens, crammed in really tight, moving around really quickly, you'll know that it's a bad idea to wear hats in a mosh pit. All right, so now that we've gone over the two different states that hydrogen can be in, we can talk about the briefest history of the universe, and it's going to be in 4 parts, starting with infancy, next childhood, then adolescence, and adulthood. All this started out 13.8 billion years ago with the Big Bang, and that brings us to our first stage of infancy. So the infant universe was very small and dense, and it had a lot of energy. It had so much energy that it glowed very brightly, and this was the perfect mosh pit scenario, where all of those protons and electrons were separated. However, this period didn't last very long at all. The universe was expanding extremely quickly in those first moments. So eventually it expanded enough that it brought us to our next stage of childhood. The child universe had expanded enough that it became completely dark and stopped glowing. What was happening on the hydrogen level is that every proton found its electron. So this period lasted for hundreds of millions of years when the universe was dark, but there was an invisible process going on due to gravity in this time. Now we think of gravity as what keeps us on the ground, but more accurately, gravity likes to stick things together, and that's exactly what it was doing to this hydrogen. So over time, the hydrogen was being stuck together into smaller and smaller regions. And this brings us to adolescence. During adolescence, these little regions became dense enough that they formed new little mini mosh pits and began to glow again. And these are the very first stars. So over time, more and more of these regions turned into stars. And that brings us to adulthood. As time passed, these stars were born, they died, they clumped together to form galaxies, and the modern universe evolved. One of these galaxies is our own galaxy, the Milky Way. So this is an artist's representation of what the Milky Way would look like if we could step outside of it and take a picture of it from afar. In one of the outer arms of the Milky Way, there's a very special star that had a special rock orbiting around it called Earth, and a weird thing called life happened on Earth, but I don't know about that. All right, so I'm interested specifically in studying this adolescent universe. I want to understand these first stars that turned on. I want to know exactly when that happened and how long this whole process of star formation occurred. The key to understanding this is light. So light is a wave that travels through space. It travels very quickly. It travels 670 million miles per hour. So to picture this, if you could travel at the speed of light, you could orbit the Earth 7.5 times in 1 second. However, things in the universe are very far apart. So even traveling at the speed of light, it can take a while to get from place to place. An example of this is the sun. It takes light from the sun 8 minutes to reach Earth. Or Alpha Centauri is one of the closest stars to Earth, and it takes light from Alpha Centauri over 4 years to reach us. So this means for more distant objects, it might take that light tens of years, even hundreds, thousands, or millions of years to reach Earth. This leads to some interesting things. If we're looking at a distant star, we're not necessarily getting the most up-to-date information. That star could have changed color. But because the light takes so long to reach us, we don't see that color change right away. It could have disappeared entirely, but we still see it glowing brightly because that light has taken so long to reach us. So what this means is that on Earth, when we look out into space, the closest stuff we see is recent from the adult universe. Beyond that, we see things from the adolescent universe. If we look even farther out, we see things from the child universe. And looking even farther, as far as possible, out into space, we can see things from the infant universe. So by looking far out, we're actually looking back in time, and we can use this very thing to study the early universe. Now I want to be clear when I put this graphic up here that this isn't exactly what the universe looks like. There aren't, parts of it that are stuck in the past or anything like that, and as much as it might seem like it, the Earth isn't in the center of the universe, and there's actually nothing special about where we are. But this is a good representation of how we observe things, because looking far away makes us look back in time. So this brings us back to our friends, Drs. Penzias and Wilson, and their telescope. What they realized eventually was that faint glow they were seeing coming from every direction was actually the glow from the baby universe. So this was a super important discovery because it confirmed some things that scientists already suspected, that the universe was once very small and very hot. The glow they saw we call the cosmic microwave background, and it really opened up a new area of research in physics. What they initially thought was a uniform glow across the sky actually has little hot spots and cold spots. And by studying these hot spots and cold spots, scientists have been able to learn a lot about the actual physics that governed this period in the first seconds of the universe. All right, so much like Penzias and Wilson, I'm interested in looking at distant objects to understand the early universe. I'm looking for the teenage universe, and unlike these two scientists, I know that signal's out there and I want to find it. I'm not just stumbling across something. So my best bet is to look for radio waves. What are radio waves? Well, remember that light is a wave, and there are different kinds of light or colors that correspond to different wavelengths. Longer wavelengths wiggle slower, and shorter wavelengths wiggle faster. We can make a chart of all the different wiggliness of light that looks like this, from the less wiggly to the more wiggly. So this is all the colors that we see with our eyes. But this is actually a very small part of all the light that there is. We have ultraviolet waves, X-rays, and gamma rays that all wiggle faster than our eyes can see. This type of light carries a lot of energy, which is why we can use it to look through, we can use X-rays to look through seemingly solid things and, for example, take a picture of a broken bone. We also have infrared, microwaves, and radio waves that wiggle slower than visible light. For example, radio waves are several feet long. We can use these different types of light to look at the sky. So this is an image of the Milky Way galaxy as we might see it with our eyes if we looked out at space on a very clear night. We can also build devices that can look at the sky in wavelengths that our eyes can't see. For example, in X-rays or in gamma rays. We can also look at the sky in wavelengths that are not wiggling enough for our eyes to see, like the infrared. Microwaves or radio waves. This picture was actually taken with data from the telescope that I use, and that telescope is called the Murchison Wide Field Array, or the MWA. It's located in the outback of Western Australia in a very remote region. It takes about 5 hours by jeep to get there from the nearest town. And the reason it's so remote is that humans use radio waves for a number of things. We use them for communication, for TV broadcasting, and also for radios, obviously. So this can cause a problem for radio telescopes because that human-made radio waves can interfere with our signal. So by making sure our telescope is very far away from all human activity, we can maximize our chance of seeing radio waves from the sky and not from humans. So this is aerial drone footage of our telescope. It consists of 200 tiles that each have 16 elements. And I actually brought one of the elements in today. So this is one of the actual antenna elements that was used out in the field. You can see that it has authentic Australian dirt on it still. The electronics inside of it tend to corrode after a while, so they get replaced out, which is why we have this one as a souvenir. So these metal arms detect the radio waves, and then that goes to a central hub, and there are wires that take that signal to a central processing area where it's digitized. And then that digital data we get at University of Washington, and we process it with custom software that we created. So feel free to take a closer look at this after the talks and play with it. Anyway. All right, so I got the opportunity to travel down to Australia last summer and help with an upgrade to the telescope. So here I am installing new components. And I'm hoping to use this telescope to find these signatures from the teenage universe. But we have this fancy telescope, we have people all across the world looking for this exact thing. It kind of begs the question, why haven't we seen it yet? And the answer is that this signal is extremely weak. And there's also a lot of stuff in the way. All the more recent stuff is about 1,000 to 10,000 times brighter than the signal we're looking for. Now, we think it's possible to tease these things apart, but we need a few things first. We need to understand exactly how this light was initially emitted. We want to know the physics that created this light. We want to understand how it moves through space and how it gets distorted as it does that. The main way this happens is that the color of the light gets distorted and it becomes redder as it moves through space, or it becomes less wiggly. We also know that the Earth has an atmosphere, and this further distorts the light. Some of the light gets reflected out into space again from the atmosphere. the light that does make it through is distorted in certain ways that we need to understand. And to make it even worse, this distortion changes day to day. So it's really difficult to know exactly what it'll be. And finally, we want to know how the light from space interacts with our telescope so we can make sense of the data we get from our telescope. So in conclusion, based on some very simple properties of light, namely that it moves through space at a certain speed, we can look back in time and understand what the early universe was like. We can actually look all the way back to the infant universe and see the bright CMB glow that came from it. We can look at space not just in visible light, but also in radio waves and other types of light. With these modern telescopes, we hope to see the signatures from the very first stars and galaxies that turned on. We haven't seen it yet, but with excellent telescopes and a great group of scientists from across the world, we hope that we will soon see this signal. And with that, I'd like to thank my research group at University of Washington, especially my advisor, Miguel Morales. I'd also like to thank the International EOR collaboration. EOR stands for Epoch of Reionization, which is just a fancy word for the universe's angsty teen years. And then I'd like to thank the Engage program and Seattle Town Hall for bringing us here, and my funding sources, the National Science Foundation and the ARCS Foundation. Thank you.